Hi everyone, this is picking up from part 4 chi-square analysis of our dog hair SNP class activity. So this section of the paper is asking you to analyze the SNP that you have found that is most strongly correlated with coat length. So if you go back, we are assuming that you have already done all of your counts at this point. Go find the one that has the most differences between it. And we want to see if this one is actually associated with the gene of interest, or if it's just coincidence that all of the dogs who have short hair have more of one nucleotide versus the other. So we are going to test our hypothesis. A null hypothesis says there's no difference. In this case, that G and T are equally likely for short or long coat. The alternative hypothesis is that there is some difference actually happening here. So it would be saying like G is linked to short coat or T is linked to long coat. These are just example ones. I'm telling you these because when we do our statistical analysis, the easiest way to do this is to say, is the null hypothesis that there's no difference actually happening? Even though we can see pretty clearly that there is a large difference between these, we want to find out if this is an actual anomaly, if it's going to be an outlier, or if this was just a random chance. If your friend came up and said they flipped a coin 3 times and it landed on heads all 3 times, you'd be like, okay, that happens sometimes. But if somebody flipped a coin 100 times and it landed on heads 99 times, you would think, okay, we need to pay attention to this. Something's wrong with that coin. But if somebody flipped that coin 100 times and only ended up with heads 60 times, we might think, oh, that's just an anomaly that happens, but that could be completely due to random chance. So the formula we are going to use here, it looks a little different than the way it was printed in your manual. The N is supposed to be above the summation symbol and the I equals 1 is supposed to be below. It doesn't matter. You're focusing on the second part of the equation here. That squiggly symbol there means sum. So chi-squared is equal to observation 1 minus expected 1 squared over expected 1. And we keep adding these together. O equals the observed count, E equals the expected count. So it looks complicated, but it's really simple. So going and looking at the locus for chromosome 32, 7473337, this should be the one that you found that was most strongly correlated with the coat length. We find that you have 9 G's with the short hair and 3 T's, and 0 G's with long hair and 12 T's. So note that that last column there is expected, not differences as shown in your numbers. I'm going to show where that number came from. So if we have our total number of G alleles, that is short plus long, 9 plus 0 would equal 9. If this were a null, if the null hypothesis were true, we would have 9 divided by the 2, and we could assume that the G's were equally spaced among the 2 versions of hair length, in this case short and long, and it would have been 4.5 on each of them. On the T's, we have 3 plus 12, and if there were no difference between these, we would have expected a 7.5 for them. So pulling these numbers up to the corner so that we can pull them as necessary. Well, that's a difference. Sorry about that little typo in the corner there. If we have our formula from the previous page, and now we have 4 nucleotides that we need to check. So if we plug in that first 9, and we say 9 minus the expected 4.5, over the expected 4.5. The next one is short with t's, that's our 3, and we would have expected 7.5. And we continue through adding in the 0 with 4.5 and the 12 with the 7.5. We can simplify these. And remember that if a negative 4.5 gets squared or multiplied by itself, those two negatives are going to cancel out. And we find 4.5, 2.7, 4.5, 2.7. Those add together to get 14.4. Okay, so what does that mean? We want to look at a chart to figure out if this is significant. To do this, we now need to figure out our degrees of freedom. This is the number of possibilities minus 1. So if you were doing a Punnett square where you had 4 phenotypes, you would have 4 minus 1 to give you 3 degrees of freedom. Here there are 2 alleles, so there's only 1 degree of freedom, 2 minus 1. And we want to know, is the number we are looking at significant? So if we look at this graph, we see that the possible results along the bottom, and thinking back to our flipping the coin, if we flip it 100 times, you're likely to get somewhere between 40 and 60 for your percentage of heads. That is more likely, it's going to be in the middle of the hump. If you got 99, you would be going way up into that very unlikely observations. And we want to know if our observed data point is in with those more likely observations or in with the very unlikely observations. So we need to find that p-value. So that is the probability of the observed or a more extreme result, assuming that the null hypothesis is true. Remember, our null hypothesis said that the G's were equal to the T's for long and short here. So what are the odds that the answers we got in the experiment were due to random chance? So we want to find something that is significant, not something that was just a little off from the more likely observations. The cutoff for most research papers is 5%. That would be p equaling 0.05 or 1% for something that is strongly significant. And occasionally you will see 0.1%. And usually on the articles, they're going to show this by an asterisk above the graph. And we'll get into that on the next discussion when we see some examples. But it's basically saying that we found something unusual in our research and we don't think it's due to random chance. We think this is an anomaly that needs to be paid attention to. So if we look at the chart, this one's a little different than the one shown in your handout, but if you'll notice, the arrow is pointing to that 5% cutoff there, 0.05, and with 1 degree of freedom, looking across that top row, we would see any p-score or chi-squared value that is over 3.841 is going to show over the 5% cutoff that we want. Our chi-squared value was 14.4. We are totally off the chart shown on here. Even if you look in the handout, it is above the 0.001 value shown. So that means that this is less than the 0.001 on the handouts table. That means there is a less than 0.1% chance that the null hypothesis was correct and that we got these results by random chance. That means we are going to reject the null hypothesis and therefore accept the alternative hypothesis was something was going on here. In this case, we can confirm that it looks like a strong correlation for the G's to have short hair and the T's to be long hair. Now, you can never use an analysis like this to prove your hypothesis, but you can usually use it to disprove stuff. So you can never prove a hypothesis, you just rule out other options. So I hope this made sense to everybody. You will never have to do a chi-square analysis by yourself on a test or anything, but if I give you a p-value and say like your p-value was 0.10, that would mean that there was a 10% chance that the answer you found was due to random occurrence. And we'd say that's not significant. So if I tell you a p-value, you need to be able to say whether it is significant or not significant. Have a good night.